Now that we've learned the limit laws, we are in a position to start looking at slightly more sophisticated limits. We begin looking at indeterminate forms. Now, there are many different types of indeterminate forms, but we will be looking at these two in particular. Now, why are these forms called indeterminate and not undefined? Well, let's take a look at something that is undefined, 1 divided by 0. If you were to answer this question, it would mean that you will have provided a number such that that number times 0 would give you 1. So which number times 0 will give you 1? There is no such number. So 1 divided by 0 is undefined. Let's see the difference between this and something that is indeterminate. So if we have 0 divided by 0 and we try to answer this question, well, that would entail finding some number which multiplied by 0 gives me 0. But now it's different. It's not that I can't find a number, it's that any number would work. So 5 times 0 would give me 0. 2,500 times 0 would also give me 0. So notice this is not the same thing. In this case, I couldn't think of a single number which multiplied by 0 would give me 1. Here, any number multiplied by 0 would give me 1. So this form is said to be indeterminate. We can make a similar argument for infinity divided by infinity. Any number multiplied by something undefinably large will give us something that is undefinably large. So let's now look at how indeterminate forms and limits are related. Let's say you have an expression and it involves two functions, f of x and g of x. Now, this expression is going to be an indeterminate form if you can't find the limit of that expression by simply finding the limits of f of x and g of x. Now, the limit may or may not exist. So how we proceed in this case is what this lecture is all about. Note if the limit of the expression is undefined, then the limit simply does not exist. So this is why it's important to be able to distinguish between an expression that is undefined and one that is indeterminate. If it's indeterminate, the limit may exist. If it's undefined, it doesn't. Here is our first example. Let's say that f of x is this expression up here and g of x is this one down here. If we found the limit as x approaches 5 of this expression here, we get 0. If we find the limit of this expression as x approaches 5, we get 0. However, if we tried to apply the limit law, we'd end up with what? 0 divided by 0, which is an indeterminate form. So how can we go about finding the limit? Well, in this case, we can see that we can simplify this. Simply dividing x minus 5 by x minus 5, as these are common factors, we get this new limit. The limit as x approaches 5 of 11 over this expression. Of course, this is easy to solve now. As x approaches 5, this whole thing approaches 11 over 70. So this is very easy. The problem is you won't normally be given the question in this form. You would most likely be given the expression in this form. So your job is to recognize that 1, this represents an indeterminate form. If you simply substitute 5 here, you get 0 over 0. You should also be able to recognize that this is factorizable, and you factorize it, bringing it to this form, and then you proceed. So I have found that many times when students say that calculus is hard, it's not the calculus that's giving problems, it's the algebra. The calculus itself is easy. It's the algebra that can give you some trouble if you didn't learn it well. So make sure you know how to factorize this and go from this to this. Because once you're here, finding the limit then becomes easy. It should be fairly easy for you to see that as x approaches 7, the numerator approaches 0 and the denominator approaches 0. So how do we tackle problems like this? We multiply both the numerator and the denominator by the conjugate of this expression here. So why do we do this? Well, because this product now of a difference and a sum is the equivalent of the difference of the square of this and the square of this. So the square of this is x plus 2 and the square of this is 9, and that difference then should give us x minus 7. And then x minus 7 divided by x minus 7 will give us 1, and so this then is reduced to this. If you're finding this very hard to understand, it's because you need to go back and review the difference of two squares. A squared minus b squared is a minus b times a plus b. So I wrote it out here to help you understand it. This times this is this quantity squared minus this quantity squared. This squared is simply x plus 2. This squared is 9. X plus 2 minus 9 is x minus 7. So this whole thing up here then becomes x minus 7 divided by x minus 7 gives me 1 over this. And of course, as x approaches 7, this approaches 9. The square root of it approaches 3. This whole thing then approaches 6. So the entire expression approaches 1 over 6. In this case, as x grows without bound, the numerator grows without bound, and the denominator grows without bound. So we are in the presence of the indeterminate form infinity over infinity. We have seen this before, and we were given the solution matter-of-factly. We were simply told, well, in such a case, since the degree here is greater than since the highest degree here is greater than the highest degree here, the limit won't exist. But let's take a closer look at this. The way we should approach this properly is to look for the term with the highest degree and then divide both the numerator and the denominator by that term. By term, I'm simply referring to, in this case, x to the 5th, not 12 times x to the 5th. So let's divide both the numerator and denominator by x to the 5th. Well, this will give us 12 here. Here we get 5 over x squared. Notice x cubed over x to the 5th gives us with x squared under here. This will be 11 over x to the 5th. Continuing down here, we get 4 over x cubed, 8 over x to the 4th, and 15 over x to the 5th. Each of these approaches 0 as x approaches infinity. So all of this then approaches 0. These two approach 0, but this approaches 12, obviously. So as x approaches infinity, the numerator approaches 12. But 12 divided by 0 is undefined. So in this case, the limit does not exist. In this case, the degrees of the numerator and denominator are the same. So you already know then that the limit of this expression then would be found by simply dividing this term by this one, which will give us 3. What we do is, as before, we look for the highest power of x and divide both the numerator and the denominator by that expression. So in this case, then we divide by x to the 5th. That leaves us with 12 plus 5 over x squared plus 11 over x to the 5th. Coming down here, that leaves us with 4, 8 over x cubed, and 15 over x to the 5th. As x grows without bound, both of these approach 0. So this entire thing approaches 12. Both of these approach 0. The entire thing approaches 4. So the limit as x grows without bound of this entire expression is 12 over 4, which is 3. The limit does exist. In this case, the degree of the denominator is greater than the degree of the numerator. So you should know that the limit of this entire expression as x approaches infinity is going to be 0. But once again, let's take a closer look at this. Here, the highest power of x is x to the 7th. So let's divide both the numerator and denominator by x to the 7th. Well, that gives us what we have here, 12 over x squared, 5 over x to the 4th, 11 over x to the 7th, and down here we have 4, 8 over x to the 5th, and 15 over x to the 7th power. Well, as x grows without bound, this entire numerator approaches 0, the denominator approaches 4. So this is very well defined. It's defined as what? 0. 0 times 4 gives you 0. So in this case, the limit does exist. And that brings us to the end of this video. I thank you very much for your attention, and I hope to see you in subsequent ones. Bye for now.